Now we are in homework 10, problem 1. In this problem, we need to explain some definitions and understandings of different examples of stochastic processes. So at first, it's Poisson process. Poisson process is such a process with Poisson distribution that, for example, the number of calls, the probability of the number of calls in 10 hours equals k equals to this. We have done much times before. So we define Poisson process xt as follow. This is the form of the Poisson process. So it has such properties. For example, if TD is no more than TC and TC is no more than TB and TB is no more than TA, we have this, and the points are independent. So the probabilities that this equals this because they are independent, and so the expected value should be lambda t, and the autocorrelation should be like this. That's the properties. And also the mean of Poisson process is lambda t, which is a linear function of t. We feel it is reasonable that the longer time we wait, the expected number of buses is larger. So that's the first process. The second process is Poisson increments. With xt, a Poisson process defined above, and sigma is more than 0, a given constant, we construct a new process yt equals this, which is the Poisson increments. That's the form of Poisson increments. So the properties, the probability that yt equals to this equals this and this, and finally we got this form, and the expected value of yt should be like this, and the result is lambda, and the autocorrelation is also like this. So we found that the mean of the new process is a constant, so we can know that the expected value of Poisson increments is only related to the density of the points in the interval that t to t plus sigma epsilon. So the third process is Poisson impulses. We define the stochastic process Zt as follows. Zt equals to this. So that's the Poisson impulses. The properties. The expected value of Zt should be lambda. It's a constant, and the autocorrelation should be like this. The expected value of Poisson impulses is also lambda, which is a constant and which is also related to the density of points in T1 to T2. So that's Poisson impulses. Then semi-random telegraph signal, and we have Poisson distribution. The probability of Poisson distribution should be like this, and there is a stochastic process that is defined as follow. Xt equals to this form. So this stochastic process is semi-random telegraph signal. The properties. For this process, when xt equals 1, the first form, the result should be like this. When k is even, and when k is odd in 0 to t, xt equals -1, and the probability that k is odd in 0 to t should be like this. So with this function, with this formula, we can get the expected value, and the autocorrelation should be like this in this form. So the mean of this process is a function of t, and the autocorrelation it's a function of the difference between T1 and T2. So the larger T and the difference between T1 and T2 are, the smaller the mean value and the autocorrelation value are. So it's not WSS we have found from this. Okay, so next is random telegraph signal. It's different from the last telegraph signal, which is semi-random. So for random telegraph, let alpha be a random variable independent of xt with this. The probability that alpha equals 1 and equals -1, each of them is 1.5. So we form a new process yt, which equals alpha multiplied by xt. So yt in this form is the random telegraph signal. The properties: the expected value should be 0, and the autocorrelation is in this form, and it's only related to the difference between T1 and T2, which is tau. So the mean is 0, and the autocorrelation is only related to T1 minus T2, the absolution. So this process is WSS. Next, random walk. This process has this form. We define xm large T equals to this ks minus n minus k, which is multiplied by s, and the result is this. So we defined xt equals to this for t in this interval, and this is the random walk, the formed random walk. So the properties: the probability that k equals to k. This is like a toss and unfair coin n times. The probability that head shows k times. So it's like the coins, the probabilities. So it's like this form. Small p is the probability the coins are its head, and q is the probability that the coins is tau. So the probabilities of this equals to this in this form, and the expected value of the random walk is 0, and the expected value of the square of x and t is this, and this is the autocorrelation, and the result is this. So from the properties and the definition, we can know that the value of this process at n large T is about the sum of the value of previous walks, and each walk is independent. The mean of the process is 0. So now finally we have Wiener process. We define Wiener process as a limiting process of random walk. So we define the WT, and it's limited xt, and s is to 0, t is to 0, and n is to positive infinity. For random walk, we have this. So from this, now for Wiener process, the expected value of this is like this, and the result is alpha t. Alpha is a constant. So we can also define Wt in this form, and with the square of s divided by t is to alpha, the constant. So the properties: the expected value, the mean of this process is 0, and the autocorrelation is this. The minimum number between T1 and T2 multiples alpha. So from the properties and the definition, we know that the mean of this process is 0, and the autocorrelation is related to the minimum number of T1 and T2, which is like a function of t. So It's not WSS, but the autocorrelation is related to T. So that's the first problem.